Okay, so what are we going to do today? In the first lecture, I actually would like to do some more examples about Newton's laws, okay? Apply it to more complicated systems. This quiz being one of the examples that I would like to solve. And in the second hour, we'll start talking about gravitation, all right? But right now, let's stick to this quiz, okay? Now, how do we solve mechanics problems? We start by investigating each movable object, each mass separately, and plotting the free body diagrams. And here, I have three masses. Now, let me start with the simplest one, M3. What are the forces on M3? There is always M3G, and then there is the tension in the rope, right? And let's say that M3 goes down with acceleration A, okay? So its acceleration will be A. How about M2? Now, let's start with the obvious one. Okay. M2G. And there must be some normal force because this is not sinking down into the first mass. Let me call that M2. But now, the friction force. Which way is the friction force acting on M2? To the right or to the left? How do we determine that? Well, intuitively, I expect this M2 to be dragged by M1, right? So it's supposed to move to the right. Okay, that's my intuition. And I would say, okay, so friction force must be to the right to cause this motion. Is there a better way to think about these things? How did we define the direction of the friction force? Let's say for kinetic friction. For kinetic friction, it was opposing the velocity of the object with respect to the surface. Okay? So, if there was no friction coefficient between M2 and M1, what would happen? M1 would move to the right, M2 would just sit there, right, if there was no friction. Which means the relative motion of M2 with respect to M1 is to the left, which means friction force must be to the right. So if you actually write a friction, let's call this 2, because it's acting on the second mass, will be to the right. How about the most complicated object in this problem, M1? Now, again, let's start with the obvious, M1G. No, there isn't M2G. We call it something else, right? M2. Okay, N2, what's N2? N2 is the force acted by M1 on M2, which means there must be a equal and opposite reaction force. So N2 must be acting down. What else though? Because this object is not sinking into the table, there must be a normal force N1 on it, right? Now comes the interesting part. How about the friction forces? How many friction forces are there acting on M1? Two friction forces. One is coming from the lower surface, the other is coming from the upper surface. From the upper surface, what's the friction force? It's exactly F friction 2, but to the left. Why? Action reaction, Newton's third law, right? So if I have friction force on a surface, if it's acting one way on the upper object, it must be acting on the other way on the lower object, right? How about the friction between the table and M1? Which way is it? To the left or to the right? To the left, it must oppose the motion of this object. So good. So this is F friction 1. Still, this problem is a little bit tricky. Because there are two different kinds of motion possible in this system. In one case, M2 may be dragging, M1 may be dragging M2 with it. So the relative motion of M2 and M1 is non-existent. So M2 is basically just going along with the lower mass. In the other case, if M1 is moving too fast, let me change the friction coefficient here, right? So if it's moving too fast, well, the upper object might be sliding with respect to the lower object. So this problem, we must make an assumption, and at the end of our solution, see if it makes sense. So here is what I'll do. I'll say, assume M2 remains stationary with respect to M1. In that case, what would be the acceleration of M2 and M1? It will be A to the right for both masses. That's very good. We've actually forgotten a force acting on M1. We've forgotten the tension of the rope, right? Feel free to interrupt me when I'm solving. I mean, it's better to get the right solution rather than the wrong solution, right? Now, okay, so let's find out. What's Newton's equation for M3? M3, I'll have M3A is M3G minus T. So let me write this as my first equation. M3A is M3G minus tension. My first equation. How about the second mass here? I have two equations. I will find N2 is M2G in the vertical direction. And in the other direction, I'll find M2A is F friction 2, right? So let me use this as my second equation. M2A is F friction 2. How about in the third, for the third mass? Well, we called it M1. Here I have N1 is equal to N2 plus M1G, or N1 is equal to, because N2 is M2G, N2 is M2G, this is M1 plus M2G. And here, how about in the horizontal direction? M1A is T minus F friction 1 minus F friction 2. Now the first friction force, F1, which is the force between M1 and the table, is that kinetic friction or static friction? Come on. M1 must be moving with respect to the table, otherwise nothing is moving, right? So it must be kinetic friction. When I have kinetic friction, I know the magnitude of the friction force right away. What's the magnitude of the friction force? It's going to be mu. I think I called it mu 2 times the normal force. But which normal force here? N1 or N2? It's the normal force for that surface. The table is acting the normal force N1 on M1. So it must be mu 2 times N1. Okay? That's great. So I actually know what this is. It's M1 plus M2 times G. Now I can add up my three equations. I have M1 plus M2 plus M3A is When I add T and F friction 2 cancel each other, I'll have M3G minus F friction 1. And F friction 1 I actually know. So it's going to be M1 plus M2 plus M3 times A is M3G minus mu2 M1 plus M2G. In other words, my acceleration is M3 minus mu2 M1 plus M2 divided by M1 plus M2 plus M3 times G. Let's find the numerical value here. Everything was given. M3 is 2 kilograms. Mu2 is 0.65. M1 plus M2 is 2 again, divided by 4, and G is given as 10. So let's see what this gives me. I think I can write this as 0.35 times 5, right? 2, 5. So it's going to be 1.75 meter per second square, right? Here is the thing though. I've made an assumption and I have not checked that assumption yet. My assumption was that M2 is moving exactly with that acceleration. So my assumption was that F friction 2 is carrying M2 with that acceleration, right? So in that case, what's F friction 2? F friction 2 is M2 times A, or in other words, it's going to be 1.75 newtons. But here is the thing. Friction force, this static friction force, has an upper limit, right? I know that F friction 2 must be less or equal to what I called mu1 times which reaction force, N2 or N1? N2, the reaction force between M1 and M2. Okay, so it's going to be, now I have N2 written here somewhere here. N2 is M2G. So this is mu1 is 0.1 M2G. So it's going to be 1 Newton. So what did I find? 1.75 is less or equal to 1 Newton. What should I do? This is wrong. I made the wrong assumption. So M2 is not static with respect to M1. It's actually sliding with respect to M1. Would that change anything in my solution? Well, the free body diagrams are exactly the same, right? But the only thing I need to change is the acceleration of M2. I know that the assumption here, let's write this in red. That assumption turns out to be wrong. So what do I need to do? I actually need to write here. I have for M2, I'm writing this again. I have M2G, I have N2. Now F friction 2 is just kinetic friction. Do I know the value of the friction force? when it's kinetic friction? Yes, I do. It's going to be mu1 times m2. So it's going to be 0.1 times m2g, which is going to be 1 Newton. Okay. So the acceleration of m2, a2 is going to be m2 a2 is going to be F friction 2. So a2 is going to be 1 meters per second square. How about the other two objects? Here for m1 I had m1g, I had n2, I had n1. The free body diagram is exactly the same. F friction 1, and I have now tension here. Here, tension minus F friction 1 minus F friction 2 is equal to m1 or m2, what was m1a. And for the third mass, nothing has changed. I again have for m3. So this is going right with a. This guy is going down with a. m3a t. So m3g minus t is m3a. If I add these up, m1 plus m3a is tensions go away, m3g minus F friction 1 minus F friction 2. Do I know what F friction 2 is? Yes, I do. This is going to be 1 Newton. How about F friction 1? F friction 1 is going to be N1 times mu2. So it's going to be 0.65 times N1 is M2 plus M1 times G. So it's going to be 2. So this is going to be 1.3 newtons. Sorry? No, we are applying Newton's laws individually to each object, right? Where is the G?
N1 is M1 plus M2. Not 1.3 but 13.
Let's see. Mu is M1 plus M2 plus times G, which is 10. You're right. So it's going to be 13 newtons. M1 plus M3 is 3A is M3 was 3G 20 minus F friction 1 is 13 newtons. F friction 2 is 1 Newton. So A apparently is, what's this? 6 divided by 3, 2 meters per second square. So if I go back and fill my table, acceleration of M1 is 2 meters per second square. Acceleration of M2 is only half that. And the tension in the cable I can easily find. Tension in the cable, I think it's the easiest to find it from here. M3G minus M3A is tension. M3 is 2, G is 10, A is 2. So it's going to be, this is 8, 16 newtons. Okay? Now, every time I have these two possibilities, I mean, obviously I solved this problem the hard way. Why? Because I made an assumption without thinking. I said, hey, let's think as if M1 and M2 are moving together. How could I have decided that M1 is actually sliding with respect to M2? What would you have done? we could have checked what's the maximum acceleration friction force can give this object. Okay? Or if you want to use your intuition, look at the friction coefficient between these two surfaces and friction coefficient between the lower surface and M1, right? It's as if the friction between an M1 and M2 is almost non-existent. It's not even there. It's very small compared to the friction in the lower surface. So if we have to guess, it was better to guess that M1 is sliding with respect to M2. And our solution would take only a quarter of the time I actually spent solving this. Okay? Nonetheless, the basic idea does not change. We take each mass individually and apply Newton's law individually. Okay? Do not go ahead and assume two objects become a single object. Okay? You cannot in general do that. Let's solve one more example. Hopefully with a better color. Okay. So let's So our standard assumptions: no friction, inextendable string, massless pulleys, find the acceleration of both masses and the tension in the rope. How am I going to solve this? Free body diagrams, right? So what are the forces acting on M1? Start with the obvious, M1G, and then there is the tension in the rope. How about for M2? What are the forces acting on M2? There is M2G, but, well, okay, so there is, if you want, the tension force here, tension prime, but it's actually just taking two tensions in the rope and just conducting these two tension forces to the mass, right? Is that point clear? I'll just write 2t here. Okay? So that part is not really very hard. But how about the accelerations? This is M2. Now, in this system, I cannot go ahead and just assume that both of these objects have the same acceleration. There's a more complicated arrangement of pulleys here. So here's what I'll do. Let's say that this guy is actually moving down with A1, and the other guy is moving up with A2. I don't know the masses, but that's what I see. What's the relation between A1 and A2? Right now, let's see. Here, if I write Newton's equations, I get M1G minus T is M1A1. And here I have M2A2 is 2T minus M2G. So I have three unknowns, A1, A2, and T, but only two equations. I need one more equation. Where would that come from? And here is my reasoning. Let's say that I moved the first mass, M1. Please stop writing and just follow this reasoning, okay? Let's say that I have this M1. let's say that I moved it up by L1. All right? In the meantime, let me say that I actually moved M2 down by L2. Now, how much has the length of the string changed? Because I actually moved L1 up, I've sort of shortened my string with L2. But when L1, I moved M1 up, so the string has to be shorter by L1. But it has extended twice by L2. What am I talking about? Here, I said it's an inextendable string. So it actually does not stretch. Which means L1 plus 2L2 must be 0. Now, what happens if I take a derivative of this relation with respect to time? I would find minus V1 plus 2 V2 is 0. If I take another derivative, what would I find? Minus A1 plus 2 A2 is 0. Or in other words, 2A2 is equal to A1. So I know a lot of you actually memorize what happens if there is a pulley which is moving twice, but also a lot of you actually just mix whether it was twice the acceleration or half the acceleration. So it's better to think about why there is such a relationship between the accelerations. If my string was extended, it was like a spring, then there would be no such relation. It's just that the force is transferred by an inextendable string here, right? So now this is going to be my third equation. First equation, second equation, and third equation. So let's solve them. I have m1g minus t equals m1. And instead of a1, I'll just write 2 times a2. Okay? So this is 1 and 3. And second equation, I'll just write m2 a2 or 2t minus m2g is m2 a2. What I can do is I can multiply the first equation by 2 and then add these up. Here is what I'll get. 2m1g minus 2t plus 2t minus m2g is 4m1 a2 plus m2 a2. T is cancelled. Here is 2m1 minus m2 g is 4m1 plus m2 a2. So a2 would be 2m1 minus m2 divided by 4m1 plus m2 times g. How about a1? a1 is the acceleration of the first mass. It will be just 2 times a2. So it's going to be 2 times 2m1 minus m2, 4m1 plus m2 times g. And the tension, I think it's best to use the first relation here. Tension is m1 g minus a1 minus a1. So it's going to be m1 g 1 minus 4m1 minus 2m2 divided by 4m1 plus m3. There is no m3. So m1g for m1 plus m2 minus 4m1 plus 2m2 divided by 4m1 plus m. And here is what I find. It's going to be 2m1 m2 over 4m1 plus m2. It's not 2, it's 3. You're right. 3m2 m1 times g. Did I find all what was of all the things that were requested? Yes, I did. I reached my goal. How about units here? What should be the unit of acceleration? It should be the same unit with g. So here I have masses canceling each other. A2 and A1 are proportional to g, which means the units are correct. How about here? Tension unit is kilogram divided by kilogram times g is meter per second square. So it's Newton. So units are also correct. How about the limits? Can anyone think of a limit where we can actually easily check that our results are correct? What happens if m2 is 1 kilogram and m1 is 2 kilograms? They should balance each other, right? So let's check. Let's check this limit. If m1 is 2 times m2, what should be the accelerations? It should be 0. The system should be in equilibrium. So let's check when m1 and m2 satisfy this relation. I do indeed find 0 acceleration. So that actually checks. How about the tension in that case? We should check if the tension gives me the correct thing. What should the tension be in that case if the system is in equilibrium? It should be just m1g. Good. So in general, this logic we've used here to determine the relation between accelerations can be generalized to more complicated systems. So on Thursday, here's your quiz question. I'm telling you what the quiz question will be. M1, M2, M3, G. And I'll tell you that M1 is 1 kilogram, M2 is 2 kilograms, M3 is 3 kilograms. And the question is to find the acceleration of m1, direction and magnitude. So this is 1 kilogram, this is 2 kilograms, and this is 3 kilograms. Now, whenever I ask this question, I would say a quarter of the students tell me, hey, there is 3 kilograms here, 3 kilograms here. So this whole thing should be balanced. Is that reasoning correct? So do you think M3 will have no acceleration here? No. Why? Because Newton's law, I can actually not apply it blindly to a complicated system where parts are moving with respect to each other. Which way do you think M3 will go? Will it go up or will it go down? It will actually go down. But how are we going to solve this problem? Now, here I have tension, right? Let me call this tension for lack of a better thing, I'll call it T2. And here I have another tension, T1. Now, the free body diagrams are very simple. Here I have M1G and tension 1 for M1. For M2, I have M2G times tension 1 again. And for M3, I have tension 2 and M3G. But now, how many unknowns do I have? Well, the thing is, I don't know the acceleration of this object. Let's call this A1. How about M2? I don't know whether it's going to go up or down. Let me just take it to go down, A2. M3, I'll also take it to go, all of them to go down. So at the end of the day, hopefully I'll find some of them to be negative, right? Not all three cannot go down. But now I have M1A is M1G minus T1. M2A2 is M2G minus T1. M3G is equal to M3A3 is equal to M3G minus T2. How many? Yes. No, it's T1. It's the same rope. Okay. So how many unknowns do I have now? A1, A2, A3, T1, T2. I have 5 unknowns, only 3 equations. There is no way to solve the system. I need more equations. One equation I can generate from the pulley here. The pulley is massless, right? So MA for this pulley is always 0, which means the net force on the pulley must be 0, which means 2T1 is equal to T2. Okay, that's good. I've reduced one of my equations. So here I have 4 unknowns and 3 equations. I need one more equation. And that equation better connect A1, A2, and A3 with each other. Right? So you have 2 days, well, 3 days, right, to figure out that equation. The first thing on Thursday will be this quiz. All right? It's not going to be a bonus quiz. All right. Take a 10-minute break, and I'll see you in 10 minutes.